Okay, great. It's great to be here at the CCA again after many years in person. I've mentioned this to some of you. This is actually the very first time that I've left the Hawaiian Islands since the beginning of the pandemic, almost 2 years ago now. So it's really great to be here in person to talk to a live audience for the first time in a while. And actually, before I dive into the science, I wanted to just briefly acknowledge the sort of extraordinarily difficult times that we're currently living in. And I thought I'd do this by showing this image. This was taken by my wife about 1.5 years ago at the Kaneohe Sandbar, which is a pretty popular tourist destination in Oahu, in Hawaii. And what you see is, of course, that the picture is deserted. There are no people. And I'm sure many of you had similar experiences in places that you have been during the pandemic, including New York City. So there's a couple of things you can take away from this image. One is that Hawaii is a pretty good place to be stuck in during a pandemic, which is true. But the other way you can interpret this image is, of course, in terms of isolation. So all of us have been really isolated in an unprecedented way over the last 2 years. And as we sort of go back to the new normal, I think it's important to keep in mind how this isolation has all affected us in different ways in terms of mental health, in terms of academic productivity, and perhaps also in terms of the way that we will collaborate in the future in some positive ways. And that is especially true for students, because we have to keep in mind that some students actually didn't even know the academic field outside of the pandemic because it's been going on for so long. So when I was putting this talk together, I was thinking about what I will talk to you about today. And I thought the best way to do this is to just give you a broad overview of the stars and exoplanet research that the group has been involved in, that helped me, at least professionally, through the pandemic, and that's our research group in Hawaii. So lots of faces on this slide. I won't go for all of them. Some of them you will know. In fact, a few people on this slide, Jamie Tayar and Lauren Weiss, have already moved on because the pandemic has been going on for so long. Travis as well, some of you may know, he started at NASA Goddard. Some of you are, of course, local. Mariam is here in the audience, is on the slide. Nick Saunders, who visited the CCA recently and will be back as well. But some of the faces on here you might not know. And so part of the talk will be about telling you a little bit about the research that we have been up to over the last 2 years. And the sort of big picture theme for our research is encapsulated in this sort of statement that we live in a golden era in galactic astronomy. And I'm sure all of you will agree with this. And perhaps the best way to illustrate this is to show this iconic image from Gaia DR2, showing billions of stars, for which we now have photometry and astrometric data. But it's not just Gaia that has made this revolution in galactic astronomy possible, but it's also other data sets, including, of course, space-based photometry from missions such as Kepler and TESS, spectroscopic data sets from Sloan, LAMOST in China, and Gaia in Australia, and other spectroscopic surveys, as well as ground-based surveys that were actually not really made for at least variable star astronomy in the first place. And those are ground-based transient surveys such as ASSASSIN, CTF, and Atlas, and I'll talk a little bit about how they can contribute to this picture as well. Kepler and TESS have really been the focus, or have sort of started this revolution in some way. And just to back up a little bit, of course, the main reason why Kepler and TESS were launched was to find exoplanets using the transit method, shown here on the left. Just as a reminder, Kepler observed about 200,000 stars in 30-minute cadence. It observed a much smaller number of stars, about 500 per quarter in 1-minute cadence. And TESS is sort of a scaled up, shallower version of Kepler. It observes almost the entire sky in 30-minute cadence. Actually, now it's more rapid than that. And it observes a much larger number of stars than Kepler did in fast cadence, with 2-minute cadence, about 20,000 per observing sector. And that will become important a bit later on. But of course, if you have a transit survey, you can also learn something about stars. I really like this animation because it actually shows these wiggles outside of the transit, and that is, of course, the stellar variability that we can learn about from high-precision space-based light curves. And so what we now have is this slew of light curves from stars. This is taken from TESS Casino, which was actually made by Megan and Ben and Adina. To my shock, I actually learned that TESS Casino is offline, so I think we need to rally some support to have TESS Casino back online. It's a great website. So anyway, I took these images from TESS Casino, and those are just light curves of random stars that TESS has observed. And you can see this slew of variability that tells us something about stars. in terms of pulsation, in terms of rotation, in terms of stellar multiplicity. And all of these aspects tell us something about the stars themselves. So we're now basically in an era where for any star that you might care about, we also have a high precision light curve. So you can think about it, for a star you have a color, a spectral type, and now you have a light curve. That tells you something about the star itself. So the three big themes of research that we're trying to combine then is, of course, exoplanets that you can study with space-based light curves. Stellar astrophysics, of course, as I've just described, you can also get out of light curves and complementary data sets, but also stellar populations, and that is the field of galactic archaeology, trying to understand populations of stars in the context of our Milky Way. Now, these fields are, of course, connected to each other, and I will point out connections between these subfields throughout the talk. And I will start with stellar astrophysics. Now, of course, stellar astrophysics itself is so big that you could probably give 10 colloquia just on this one topic. So I will only focus for now on the one field that's near and dear to my heart, as many of you know, and that is astroseismology. So to back up a little bit, what is astroseismology? It's the study of stellar pulsations. The stars pulsate for a variety of reasons. When they do, they produce intensity variations as a function of time. So this is just a light curve. This is actually a light curve of the sun in integrated light, where you can see the variations due to the pressure waves that are propagating through the interior of the sun. We analyze that data most of the time in the Fourier domain. So you take a Fourier transform of your data set, and what you get for the sun is then this broad picture of peaks. And each of these peaks in this Fourier transform is basically an individual pressure wave that's propagating through the interior and tells you something about the interior. And the way this works is that the frequency depends on the sound speed itself depends on the interior composition. So measuring the frequencies, you're in principle able to back out the interior structure and also more globally fundamental properties. So the cool thing about astroseismology is that almost all stars in the HR diagram pulsate. So this is a diagram a few years old now, an HR diagram showing all the different pulsators across the HR diagram. There are many different types. So of course, the sun-like stars live down here. There's also a lot of massive star pulsators. I won't be talking about those today, although there were some really interesting developments on these in the last few years, and of course also all the way to white dwarfs, which also pulsate. But the ones that were the most popular, at least in the last 10 years or so, are the so-called solar-like oscillators. So these are stars similar to our sun, where the oscillations are driven by turbulence in the outer convection zone. So this is an example. This is actually not the sun. This is a Kepler star, although it almost looks like the sun because the signal to noise, the integrated sun, because the signal to noise is so high. So this is a Kepler star showing this really nice regular series of peaks that we observe for these solar-like convection-driven oscillators. And this is actually the main reason why they have been so popular, and where most astroseismology results that you've probably heard about come from these convection-driven oscillations, because these patterns allow us to do what we call mode identification. So we can determine, based on the patterns, which of these peaks corresponds, for example, to a dipole mode or to a quadrupole mode or a radial mode. And that is key. You need to be able to do this in order to compare the oscillations of frequencies to the models and do astroseismology. So solar-like oscillations have been really popular for this reason. There's another reason, which is that the regular spacings that you observe can be translated to fundamental properties in fairly simple ways. So there are several regular spacings. You can measure the so-called large frequency separation, which is the mean separation between modes of consecutive overtones and the same spherical degree, so consecutive dipole modes. Delta nu scales with the square root of the mean stellar density, which is fairly well known. There's also a second relation, which is the so-called nu max relation. So that nu max is basically the peak of this envelope, so the frequency at which the oscillations reach a maximum power. That scales with the surface gravity of the star and weak dependence on temperature. And then for some stars, you can also measure the so-called small separation. So that's the separation between modes that travel to different depths within the star, and that gives you information on the age, because it basically senses the compositional gradients within the star. So Kepler has really revolutionized our image of solar-like oscillators, and this is shown in this diagram. This is our two HR diagrams. On the left is the field, the state of the field in 2009. It's not that long ago, only a little bit more than 10 years ago now. Those were all the detections of solar oscillations we knew back then. So we're, a dozen or so main sequence stars and half a dozen or so red giant stars. And with Kepler, this has completely changed. On the right-hand side, we now have thousands, tens of thousands of detections. The reason, by the way, why there are a lot more red giants here is because red giants have larger amplitude. So this is a detection bias. They're easier to detect than the main sequence stars that are less numerous. So Kepler has been really revolutionary. You might ask yourself, well, what can we learn from TESS about these sort of stars? And for TESS, the main advantage is, of course, that we can apply astroseismology to stars that are much more nearby and better understood through other means. So one example is this discovery of oscillations in Alpha Mentae. This is a paper led by Ashley Chontos, who's a finishing grad student at UH at the IFA. The detection, the astroseismic detection is shown here on the bottom left. This is a little bit different than I've shown before. It's the power spectrum in a log-log scale. But the power axis you're looking for is basically up here at very high frequencies, about 3,000 microhertz, which is similar to the sun. And the right-hand side graph actually shows why this detection is special. It's basically one way to illustrate the astroseismic population that shows the stellar radius, so the radius of the star as a function of the distance. And if you look at this, all of the Kepler detections have shown it before are around stars that are fairly faint and fairly far away. So the symbol size also correlates with the V magnitude of the star. And you can see that Alpha Mentae, which is the star that we've detected oscillations in, is now the closest star for which we can do astroseismology with space-based photometry, detailed astroseismology. We can measure frequency spacings and so on. So TESS, which are the orange points here, are really filling in the parameter space of nearby stars that are well characterized, to which we can now apply astroseismology. And this is one example. We're still plowing through a lot of the data. I expect that this diagram will be filled in with a lot more detections over the next few years. Now, moving on a little bit, so the solar oscillators is what usually everyone talks about, but I actually want to talk about a different type of pulsating star that has where TESS has really made a breakthrough recently, and those are delta Scuti stars. So moving a little bit from the cool stars, a little bit hotter into the instability strip, we get to the delta Scuti stars. These stars are basically near the zero-H main sequence in the instability strip, so a little bit lower than Cepheids and our Lyra stars. And they've been known for a long time, over 100 years or so, because their amplitudes are actually quite large. But the problem has been that we weren't able to really apply astroseismology because we didn't have any regular patterns that we could use to do mode identification. So this is a frequency spectrum of one of the most famous delta Scuti stars, FG Vir, has been observed for a really long time using ground-based observations. Many, many, many frequencies have been detected, but there are no patterns, and we can't use, there are some ways to discern which modes are which, but it's really, really difficult, even if you remove the combination frequencies, which are in the bottom here. So one of the breakthroughs that have happened in this field recently was that we have discovered a subset of delta Scuti stars for which regular spacings have been detected. So this was first reported in this Nature paper led by Tim Betting and also some of people in our group of the discovery of regular high frequency pulsation modes in delta Scuti stars. So you might ask yourself, how did we miss this all these years? Why did we only discover this with TESS? And the reason for this is that these regular spacings in delta Scuti stars only appear at high frequencies. So here are some examples. Each panel shows a power spectrum of an individual delta Scuti star observed by TESS. And just to illustrate, right, these look much, much nicer. They have a lot of regular spacings that you can sort of pick out by eye. And they have a much more regular structure than the star that I've shown you before. And the reason why we didn't really recognize this with Kepler was that most of the stars that Kepler has observed were observed with 30-minute cadence. And the Nyquist frequency for 30-minute cadence is about here. So that means to unambiguously identify a pulsation mode, your frequencies need to be lower than this limit. So the high frequencies at which these stars oscillate were really sort of opened up by TESS and by the 2-minute cadence data that TESS has collected for so many stars. Now, one cool thing about these stars is that in addition to being high frequency and having regular spacings, one thing that we found out is that they seem to be preferentially young. So if you plot them on an HR diagram, what you see is that these high-frequency, nice delta Scuti stars, as we just call them, are mostly located near the zero-H main sequence, which is for solar metallicity shown by this black line. So these are young stars. So the young A stars are those that preferentially pulsate at higher frequencies, and if they pulsate at high frequencies, they show regular spacings, and that means that they're now amenable to the astroseismic tools that we've been applying for the cooler stars for many years. So this has opened up a huge amount of very exciting parameter space, and we're really just scratching the surface of this. So here's some very first results on this. This is work led mostly by Simon Murphy at the University of Sydney. The left-hand side shows a delta Scuti star in upper Sen Lupus, which is a subgroup of the SCO-Sen association. And this is showing basically a chi-squared, a seismic chi-squared, fitting frequencies to models as a function of age. And you can see that if you can do this mode identification, you can actually get a fairly precise constraint on the age, so a fairly small number of modes that give you a relatively good fit to the frequencies. And from this, Simon's derived an age for this subgroup with about 10% error bar, which is pretty good. Of course, you can get ages also for moving groups and so on from isochrone fitting, but this is a completely independent way to do this. And this is only the beginning. You know, we have A stars in most associations, and we will likely be able to apply this for most other associations that we know of. On the right-hand side, this is actually an unpublished result that we're working on at the moment. That's very exciting. This is an incredibly rich power spectrum of a delta Scuti star. So here's the power spectrum. That's just a light curve on top. It's about 38 identified pulsation modes. It's the largest number of pulsation modes ever individually identified in a delta Scuti star. This is a star that has a debris disk. All of them are young, remember, so most of them actually still have disks around them in which planets are forming. And in addition, it's actually a debris disk that's rich in CO, and there have been some theories as to why relatively old stars still have debris disks that are rich in CO that might, you would expect that actually disperses fairly early on. There's some theories about secondary processes that could produce this CO in these debris disks. And putting an age on this star will help to discern which processes might be responsible for this. So I think for these A stars, for the whole delta Scuti stars, this is just the tip of the iceberg, and you can expect a lot more exciting results coming out of this over the next few years. Okay, so I've talked about stellar astrophysics and astroseismology, and I want to move on to the first synergy, and that is the synergy between astroseismology / stellar astrophysics and stellar populations. And this is, of course, something that a lot of people here are interested in. It's just the intro slide is, of course, the fact that in galactic archaeology, we want to reconstruct, in some ways, the formation history of our own galaxy. So we have the different individual components, the thin disk, the thick disk, the stellar halo, and various subgroups kinematically and chemically that we can distinguish. And the big picture questions are, whether there are any mergers in the galaxy that have happened and how these mergers have affected the evolution of our Milky Way, how old are the individual components in our galaxy, and how did the stellar halo form? For all of these questions, as the name galactic archaeology implies, ages are critical. And that's exactly where the stellar astrophysics component, of course, comes in. So one really neat aspect of this synergy is that spectroscopy and astroseismology are actually very complementary to each other in terms of deriving ages and fundamental properties of stars in general. This is particularly true for red giants. Of course, we focus on red giants because they're fairly far away and probe large distances. This is an example of how you can add this information to get a lot more out of your data. So on the left-hand side, it's just a regular HR diagram of the giant branch if you just use photometry. It all looks pretty scattered, not much you can do. In the middle panel, you then add spectroscopy that really shrinks the error bars and the temperatures. You can measure those very precisely. And then on the right-hand side, if you add astroseismology, you shrink the error bar in the y-axis and log G in particular, and you can actually, by eye, just pick out evolutionary phases. So this is, for example, the red clump, where red giants start burning helium in their core. So the synergy is really powerful. You get from seismology, you get the density and log G. From spectroscopy, you get temperature, metallicity, and abundance information in general. You combine those two, you get radius and mass. And for a red giant, if you have the mass and chemical abundances and metallicities in general, you can back out an age. So this has been done for a large number of stars that has sort of kicked off galactic archaeology. Of course, galactic archaeology has also been done using spectroscopy alone. I won't be talking about this too much today, but the synergy between the two has really allowed us to place very tight age constraints on stellar populations. So this is a study, one of the first, I'm not sure whether it was the first, but one of the first that have actually done this in a systematic way. So the left-hand side is the chemical abundances of red giants in the Kepler field. So this is combining the Apogee survey with Kepler, the APOCAUST project. And basically the way that we use the alpha abundances and metallicities is that we separate populations in the high alpha abundance population and the low alpha abundance population, which is often also loosely associated with the thick disk and the thin disk in the galaxy. And what we can do with astroseismology, which we have for all these stars, is we can actually derive ages. And back in 2018, this was done using this population, and we see clear evidence that there's actually a bimodal distribution where the high alpha sequence corresponds to old ages and the low alpha sequence corresponds to younger ages. This has had a lot of really interesting consequences, including actually age dating mergers. So the Gaia and Enceladus discovery of Gaia, and age dating when Gaia and Enceladus actually happened. This can be done using individual stars that you think were originally from Gaia and Enceladus and in situ stars. So I have some papers here on the right. Sam led one of those that attempted this using individual stars as well. And all of the studies roughly agree that Gaia and Enceladus happened around 8 to 10 giga years ago. And this is sort of pinpointing the timing of these mergers is something that astroseismology can do. And as we push further out, we'll be able to do for more and more of these mergers that have happened. There's also an interesting subpopulation of these young alpha-rich stars, which is the second peak here. So one of the leading theories is that these might be basically the remnants of stellar mergers. So the stars appear more massive than they actually are. So the astroseismology gives us a younger age. Yep.
We have a question from Adrian online.
I have to channel Rosie Wise, hey Dan, who would say that the young alpha-rich stars are actually just anomalously massive and not necessarily young.
Interesting. Yeah.
Would you agree with that?
Yeah, I'm not totally up to date on the latest literature. I do know that the stellar merger theory is not the only one. I know that there are other opinions on this. I mean, I think that the astroseismic ages are what they are. So for some, that means, the masses are what they are. So whatever leads to the more massive than usual masses is, there could be numerous ways you can get there. So stellar mergers is one, but perhaps they're just unusually massive. So I don't.
Okay, fair enough.
I can't take a side on the controversy on this, but I agree. Yes, you're right. There's more than one explanation for this. Agreed. Okay, so this was with Kepler, and with Kepler we've done this actually 1,000 red giants. I think that was the APOCAUST catalog when this paper was written. We now have more than that, but there's an additional data set that has since become available from the K2 mission, and that is the K2 Galactic Archaeology Program. So that basically makes use of the fact that Kepler broke and started observing various fields across the ecliptic plane, which is shown here in this diagram. I actually won't talk a lot about the K2 Galactic Archaeology Program out of time reasons, but Joel is, here in the audience, is one of the leaders of the K2 GAP program, together with Sanjeev Sharma at Sydney and Dennis Stello. And so there's a lot of exciting results coming out of that. The astroseismology for K2 is, of course, a little bit less informative than Kepler because it's a shorter time span. But there's still very exciting results coming out of these campaigns as well. So what I will talk about is what TESS can contribute to this picture. So TESS, of course, can contribute to the fact that we're not constrained to a given field in the galaxy. Kepler was constrained to a single field, K2 was constrained to the ecliptic plane. But with TESS, we're actually not constrained, well, at least soon, to any fields at all, because TESS is observing almost the entire sky. So one of the things that we have worked on, and this is led by Mark Hahn at UH, is an all-sky catalog of astroseismic detections from TESS. So this is in an animation that we made based on the detections that we had. Those are 160,000 oscillating red giants that have been detected with TESS using the first 2 years of data from the mission. And you can see as this sort of animation plays through and fly through the galaxy that the distribution of the stars is more or less uniform. There are few gaps here and there because of observing the pointing strategy of TESS. And of course, one of the other things, for those of you who are familiar with the field, is that the distance reach of the TESS data is not as far as K2 and Kepler, and that's just because TESS is on average observing brighter stars. But still, with TESS, we now actually have the first sort of all-sky galactic archaeology picture with astroseismology, and for a subset also with spectroscopy. So here are some detections for those of you that in the know with astroseismology. So these are power spectra of individual red giant stars observed by TESS. What we measure from these data sets, because we only use single sector data, so this 27-day data only, is we only measure the peak envelope, so this nu max parameter that I mentioned before. So the nu max parameter for all these, in all these power spectra, you see the granulation. So this is the 1 over F noise that comes from granulation. On top of that is the oscillation excess, which is what we're detecting. So this becomes harder if you have higher nu max stars. So these are lower luminosity stars that are faint or more difficult. That's just a detection bias. And higher luminosity stars of larger amplitudes, so you can detect them out to fainter magnitudes, which are here on the right. So we've done this for 160,000 stars. This is an order of magnitude more than the Kepler and K2 yield. And importantly, it's all sky. So one cool thing that we can do now is that we can actually put all these stars, all sky, and we can ask, well, do our astroseismic detection follow some astrophysical expectations from how our galaxy formed, for example? So this is actually an image of the TESS full-frame images. So these are images from TESS taken with the scanning pattern of TESS. This gap here will be filled in soon in the TESS extended mission, but has not been filled in with the data set we used. So what I'll do next is that this will switch into a map of stellar masses determined using just the nu max measurement that I've just shown you. So this is using nu max, which depends on log G, combining it with a radius from Gaia to back out the mass. So if I switch to this, this is the map that we get. And to give you a scale for this, this is the color bar gives you basically the mean or the median mass in each of these pixel bins. And what you can see is that the lighter colors or the greener colors are higher mass. So these are younger stars, and the bluer or darker colors are lower mass stars. So these are older. And what you see here is, of course, the expectation that the younger stars are all closer to the galactic plane, and as you move away from the galactic plane, you get to older and older stars. So this might not be necessarily that mind-blowing because it's expected, but my mind was actually blown when I first saw this data and thinking about how it was derived, because there's almost no model dependence in there. You just take the TESS light curve, you measure the peak of this power excess, you get a radius from Gaia, which has a little bit of a model dependence, but not too much, and you plot it on the sky, and you get basically the age gradient in the galaxy straight out of this. Without too much model dependence. So again, this is sort of the tip of the iceberg. There's a lot more you can do. We did a little bit more sort of astrophysical validation of this data set. One of the cool things you can do is you can plot the stars in a tumor diagram to pick out halo stars. So these are stars that we're particularly interested in measuring ages for. So if you do reasonable cuts in this parameter space, you can sort of identify the disk and the halo, and we've identified about 350 new astroseismic halo candidates in this catalog, which is, again, a large increase in terms of number compared to Kepler and K2. You can also plot velocity dispersions, which is shown on the right here. So this is some normalized version of a velocity dispersion as a function of the mass, both in the radial direction and in the z direction. And you can see that, as expected, the velocity dispersion increases for lower mass stars. So older stars have higher velocity dispersions, basically because of the kinematics and the kicks that have been getting throughout time in the galaxy. So again, these are all sort of things that we would expect, but it shows you that a relatively simple measurement from TESS can give you very powerful information. And this is, again, just the tip of the iceberg. We've only used the first 2 years of data. There will be a lot more of this as we move on. I do want to briefly also talk about new data and tools. Since I'm at the CCA, I want to throw out some challenges in terms of how we analyze our data. A lot of astroseismology and a lot of the archaeology is done using Kepler and TESS, but that's actually not the only data set we can use for this. So on the left-hand side is an example of using M giants. So these are very evolved stars that are near the tip of the RGB almost, and trying to do astroseismology of these stars using ground-based transient surveys. So this is data sets like Assassin, Atlas, CTF. And in the top left is a power spectrum. This is work also led by a UH grad student a few years ago, Connor Augie, where we tried to back out, see whether we can back out the same answer with Kepler and with these ground-based surveys. And the answer is yes. Basically, these peaks that we see with Kepler, we cover the same peaks using these much more sparser data sets. And this is really powerful because Atlas and Assassin can observe to very faint magnitudes, and the amplitudes of these M giant pulsations are quite large. So that means you can increase the distance reach of astroseismology by a large factor. So basically, if you say, okay, you use these ground-based transient surveys and you can do astroseismology of M giants, you can get out to about 50 kiloparsecs. So this is a simulation. This is a collaboration with Robin Sanderson, where we compared the astroseismic distance reach, which is here, about 50 kpc, compared to the distances that Gaia gives us. So we can basically, with these ground-based surveys, which are all sky as well, increase the distance reach of at least determining distances to stars, maybe even do more. The challenge is, of course, that high luminosity red giants are difficult for other reasons. How do we actually translate the seismic information to distance and mass? That's not quite worked out. But there's a huge potential here. I think that's really untapped. And on the other side, on the right, this is work led by Mariam here in the room that is using granulation. We always think that we need to detect oscillations to get the fundamental stall parameters, but that's actually not true. You can also just basically model this 1/f noise, the granulation background, on top of which the oscillations sit, and that is also sensitive to surface gravity. And the key is that this you can do to much lower signal to noise levels than the astroseismology. So that again opens up a much larger sample. Both of these projects, by the way, came up in SciLog meetings that some of you might have heard about. So these are sort of higher risk experimental ideas that we've been working on, and I'm still excited to pursue. Okay, I'm going to move on and talk a little bit about exoplanets and the connection between stars and planets, which is something that, of course, many of you will know, that you only know your planet as well as you know your star, and that the reason for this is because we measure most of the planet properties relative to the star. Gaia has again been a huge driver of this, and the reason for this is that Gaia measures distances to basically all exoplanet host stars. I shouldn't say all because some of them are too far away, the microlensing detections, for example, but for all of the transit and rate of velocity host stars, we now have a really good distance. And that means that you can, of course, calculate the radius of a star if you rearrange the Stefan-Boltzmann law, which depends on the bolometric flux, the distance, and the effective temperature. The distance we now know to most stars to like 1% or better from Gaia. That doesn't necessarily mean that we know the radius of the star to infinite precision, and I like to point this out often, that the bolometric flux and the effective temperature both have systematic errors that are non-negligible. So photometric 0 points, for example, set limits of a few percent on the bolometric flux. The accuracy of interferometric angular diameters sets an accuracy on the temperatures to about 2%. That still means that we can get the radii to about 4%. If you're interested in the sort of systematics discussions of where that comes from, I encourage you to read a paper that Jamie Taylor led last year that discusses these sort of temperature and bolometric flux difficulties. So again, it's still pretty good. We can measure radii to 4 to 5%, which is excellent compared to Gaia. But if anyone tells you that they've measured the radius of a star to 1% or better, I would be very cautious with that claim. But 4 to 5% is still very good, of course, and that means that we can make beautiful HR diagrams of stars, including those that host exoplanets. So this is the PhD work by Travis Berger, where we've basically took the Kepler sample and re-derived stellar radii and temperatures. In this case, this is actually a straightforward application of the Stefan-Boltzmann law. There are no models or little models included in this, but you can really nicely separate, of course, the different evolutionary states that we see. Now, that, of course, then translates into properties of planets. So this is actually, I think, the first graph I'm showing with planet properties on it. And so this is showing the radius of the planet on the y-axis, large planets being up here, small planets being down here, and the incident flux on the x-axis. And this is actually plotted in the way that hot planets are on the left and cool planets are on the right. So that means cool, small planets are down here. Those are hard to detect. And so this gap here is entirely a detection bias. The colors on this plot are the status of the planets. So red are confirmed planets, black are candidate planets. This is the Kepler sample. For our purposes, we can assume that those are basically the same, but this is a distinction that's sometimes important to keep in mind. So this is the distribution of Kepler planets before Gaia. And what I'm going to show next is the same diagram, where the only thing we've changed is the radius of the host stars from Gaia, and we've recalculated the planet radii based on that. So if I switch to this version, and I will flick back and forth between those two a couple of times, you can really nicely see that by just changing the stellar radius, nothing else, so this is not changing the transit depths or rederiving anything from the transits in a particular way, you see a couple of things that sort of snap into focus in this demographics picture and become a lot clearer, which immediately tells you that most of the features were washed out by our uncertainties in the stellar radii. And the most famous by now, of course, many of you will know about this, a feature in this diagram is this dearth of planets around 2 Earth radii or so at high incident fluxes. So this is a gap in the distribution of small planets, or a valley if you observe it as a function of period or incident flux. This feature was actually discovered prior to the Gaia data release, shortly before the Gaia data release, based on a subset of Kepler planet host stars that were spectroscopically characterized much more precisely. This work by the California Kepler survey, and this is the plot showing this result. This is basically the same as I've shown on the left, but collapsed along the incident flux, showing these two peaks in the radius distribution of exoplanets from B.J. Fulton's paper. And so the current interpretation of what these two peaks are is basically that the larger radius peak consists of planets that have some kind of rocky composition in the core and some kind of volatile envelope made out of hydrogen helium that gives them the larger radius. And the smaller peak, so the one at around 1 Earth radius or so, consists of super Earths, which are basically planets that have lost their volatile envelope through some process. Now, there's still some theories as to how these populations actually came to be. I think there is now pretty strong evidence that both of these basically come from one family initially. So basically, one of the theories is that you start off being a sub-Neptune with some kind of hydrogen helium envelope, and then you evolve to become a super Earth. And the mechanism with which the envelope is lost is still under the debate. Some of the theories predict that this happens relatively quickly through photoevaporation, so some high energy radiation stripping the atmosphere, and other theories predict that this is a relatively slow process that goes on over gigayear timescales, where the envelope gets lost due to the luminosity of the core. So one of the things that's important to discern these theories is clearly age. How quickly do these populations, or these two peaks in this radius distribution, change? And one of the exciting discoveries that was made over the last few years, and this is again from Travis's thesis work, is that it seems that this process, that there's actually a change in the distribution of radii that goes on over gigayear timescales. So this is the same diagram showing the two peaks in the radius distribution, but now splitting the sample into young planets. So these are planets less than a gigayear old or so, and old planets that are older than about a gigayear. And you can see that in the young planet histogram, you have a larger fraction of sub-Neptunes than super-Earths. In other words, the ratio of super-Earths to sub-Neptunes increases at old ages. And so that is some evidence, we interpret it as evidence, that there's an evolution of planets from the super-Earth, for the sub-Neptune peak to the super-Earth peak over gigayear timescales. So there's been a lot more work done on this. So again, this is sort of going back to what I described before. This still doesn't actually answer this question of what's causing the mass loss, unfortunately. It could have, you could have this mass loss go on relatively quickly. So that means that you move, over here in 100 million year timescales or so. But it could also be that you move slowly over gigayear timescales. That's initially how we interpreted it. But there's also a way that you can actually have fast mass loss. So you move from sub-Neptunes to super-Earths relatively quickly, but then you replenish this peak of sub-Neptunes by larger planets that cool and contract over long timescales. So this sort of course, 1 gigayear separation is not quite enough to really clinch, which theory is the dominant one, and perhaps both of them act in this. There's been a lot more work on this. In fact, Trevor has worked on this as well, using isochrone ages, which we used here, but also rotation-based ages, which is another very powerful diagnostic. There's now evidence that this whole valley actually shifts to smaller radii at young ages as well, which is again consistent with some kind of slow process over gigayear timescales. But I think I think age is a super exciting dimension in this whole question, and we think we need better ages. I'm not quite sure how we will do this. I think with rotation gyrochronology is certainly one way to do it. We need more planets around young stars, which TESS is actually giving us. There were a lot of exciting discoveries coming out of this. But I think in general, we just need a better age resolution, and that's a really interesting challenge. Another way to make progress on this is to actually measure masses of planets, because the mass loss depends on the core mass of the planet as well. So finding multi-planet systems, measuring masses, and then modeling how they lose their mass is another way to get at this problem. Okay, I've talked a lot about small planets. We also work on large planets, so gas giant planets. They're also interesting for various reasons. I won't be talking about this too much. So this is a survey to find giant planets transiting giant stars. This is something that Sam has been working on for a long time, and I'm sure he tells you about it frequently. Nick Saunders has been starting to work on this also for his PhD. So this is a project to basically mine the TESS data to find large planets orbiting large stars and trying to discern the effects of stellar evolution on properties of gas giant planets. So it includes the inflation of radii, it includes the orbital architectures, and it includes occurrence rates. Basically, what is the influence of main sequence evolution on the occurrence rates of planets. So I'll browse through this because Nick will be back to tell you more about it, and Sam will keep you updated on this as well. Instead, I want to just briefly highlight a couple of other projects that we're working on. So this is work by Jingwen Zhang, who's also a grad student at UH. She's working at architectures of TESS planets. So there's a lot of interesting science questions with respect to planet formation that you can answer with orbital architectures. So one system that she's worked on is a misaligned multi-planet system. So this is sort of sketched up here. You have the star, 2 inner planets that are transiting with Kepler. And we've detected a misalignment using astroseismology to get the spin axis inclination. And one cool thing is that we've discovered that there's an outer perturber. So this is sort of this green sketch here. These are the radial velocities of this outer perturber with a very long period. And we believe that it's this outer perturber that has tilted, that is basically responsible for torquing the orbital plane of the inner planets and causing this misalignment. This is really interesting to sort of compare misaligned multi-planet systems of small planets with the misalignments that we see in hot Jupiters to sort of discern whether the misalignments that we observe in hot Jupiters are actually due to are related to their formation. One of the things that Jingwen will do for her thesis is actually extend this to TESS. There's really neat stuff you can do by combining Hipparcos, Gaia, astrometry, so accelerations that we can measure with Hipparcos and Gaia, and radial velocities to work out the inclination of a binary perturber to the inner transiting planet. And that's something that we can do with TESS and that you will be working on. Another quick highlight, and again, I won't talk about this in a lot of detail, is the TKS survey. So this is a large collaboration of institutions to measure masses of exoplanets observed by TESS. Again, this is sort of an ongoing program. One paper that recently came out that describes the surveys led by Ashley that sort of shows the sample that we're investigating. So on the left-hand side is an HR diagram of all the exoplanet host stars that we're measuring, trying to measure masses for. So this includes a broad range of spectral types on the main sequence, but also some evolved stars, some subgiants. And on the right-hand side is again a radius versus flux diagram showing the planets for which we are trying to measure masses for. Some results already trickling out of this. I won't go into detail in it, but there's a lot of results to be expected from this, including some hints as to related to the radius gap question that I've talked about before. We can actually measure masses of planets on both sides of the radius gap. Now, the last thing about exoplanets I want to say, at least in terms of work we're currently doing, is actually a very exciting result that we're also still working on, and that is led by Casey Brinkman, who's a PhD student working with Lauren Weiss at Notre Dame and myself on measuring masses of small rocky planets. And this is a particularly exciting system that we've been following up for a while. The host star is actually alpha rich, so this is again our alpha Rn versus metallicity diagram, and it's quite alpha rich and metal poor, which means that it must be quite old. We estimate about 10 gigayears or so. And it has multiple planets, including a small planet that is fairly close to the star itself. The temperature of the planet is about 2,500 Kelvin. So this is a planet that's really close in to the star. And what we have achieved using Maroon X, which is a new high precision radial velocity spectrograph from Gemini, is that we have a mass measurement of this planet. And intriguingly, the mass measurement implies a very low density of this planet. So this is shown in the main plot here. This is the planet density versus radius. And the inner planet B sits here. And these are some composition curves. So basically, if you just look at this green line here, it is a solid rock. And the planet measurement is basically significantly below this. Now, normally, you would not be that excited. You would just say, OK, well, it's got some kind of volatile atmosphere. It's fine. But this is an extremely hot planet. And so it's very unlikely that this planet has a hydrogen helium envelope. So, but its density implies that it must have some kind of atmosphere. So we currently hypothesize that this might be some kind of non-primordial atmosphere that's made out of outgassing of magma or some other solid material in the planet. We're working with Edwin Kite at University of Chicago on this, and this is something that we're quite excited about, and you will hopefully be able to read about soon. Okay, let's see. In the last few minutes or so, I want to talk a little bit about what's next, what I'm excited about in the next, 10 years or so, or maybe even longer. Of course, if you talk about this with exoplanets, you show this sort of, mission timeline of missions that NASA is planning. Kepler and TESS are, of course, already operating. JWST, I should knock on wood, will be operating next week or so. We have the Roman Space Telescope, and of course, what's called on this chart still the New Worlds Telescope, which is of course one of the top priorities in the Astro 2020 decadal, which is sort of a mix between HABEX and LUVOIR to directly image exoplanets. And I've pulled this from the Astro 2020 report. This is sort of a simulation of what this might look like, the solar system at 12 parsec as seen with some version of LUVOIR. And the goal is, of course, to image in reflected light Earth-like planets. And by necessity, one of the things that we need to do in order to achieve this is we need to look at very nearby stars, because those are the ones where we can get the angular resolution to actually get close in enough to find planets at AU spatial scales. And so that means that characterizing bright stars will be really critical for the direct imaging community of exoplanets in the upcoming decades. And bright nearby stars are exactly the sort of stars that we are in the stellar community and in the astroseismology community are most excited about. So this is a paper that I published earlier this year, which looks at bright stars using TESS 20-second cadence data. This is a new data product by the TESS mission. It turns out that the 20-second cadence data gives much better performance for bright stars than the regular 2-minute cadence data. This is shown in this plot. It shows the scatter, so the RMS of the light curve, 20-second data compared to 2-minute data as a function of TESS mag. And at the brightest stars, 6 magnitude or so, you get an improvement of 30% or so. Basically, it has to do with the way that the cosmic ray rejection is done and how that interacts with pointing jitter for bright stars. But I won't go into detail on that. I'll just mention that this allows us to do astroseismology of bright sun-like stars that wasn't possible before. So on the right-hand side here are 2 sun-like stars at 10 parsec, so sort of, prime targets for direct imaging. And the bottom power spectra are using the 20-second data, and the top panels are using the regular 2-minute cadence data. And you do much better using the 20-second cadence data products. And we can expect to do this for a lot more stars as the TESS extended mission goes on. You can also do astroseismology using radio velocities. There are a lot of great chats already today about this. You don't need to use photometry. You don't need to use space telescopes. You can also do it if you have a really high precision radio velocity spectrograph. You can either do this by putting one of these highly precise spectrographs on a large telescope with a short readout time. So the Keck Planet Finder will do this. This is led out of Caltech. That will be commissioned next year. So basically, you just stare at a star and get really high cadence, high precision radio velocities. The other way to do this is to build a network of telescopes that are smaller to observe a star continuously the entire time. So this is the goal of the SONG network. They already have nodes in Tenerife, Australia, China, and we're hoping to build one in Hawaii eventually. And in both cases, one of the effects is that the signal to noise of the oscillations is much higher in velocity than in photometry. That's because the granulation effects are much smaller, and it allows you to do astroseismology of sun-like stars. So the right-hand side here are just some simulations of oscillations with KPF of free nights of nearby sun-like stars that will be prime targets for direct imaging. Okay, and the very last thing I will say is this synergy. I haven't talked about this yet. Stellar populations and exoplanets. That's a bit, super big picture, but I'm pretty excited about it. I've showed this image many times now. What if you think about exoplanets on a galactic scale? So these are all transiting exoplanets from Kepler, K2, and TESS, projected just put onto the Gaia map. That's of course a bit misleading because the stars are actually at vastly different distances, and most of the TESS planets are quite close. But I think we can start thinking about this, and it's actually not too early to start thinking about the exciting science we might learn. One thing that I will briefly mention is actually Roman. The Roman Space Telescope could be really exciting for this. This is something that Ben Monte and I have thought about a little bit recently. It turns out that the Roman Space Telescope footprint is almost perfectly matched to globular clusters. So this is 47 TOC and NGC 6752. And so if you point Roman at a globular cluster and do time series photometry, you have a lot of stars, as shown in the CMDs in the middle, and you can actually do astroseismology of red giants, which allows you to answer interesting questions such as where the multiple stellar populations in globular clusters might come from by measuring masses. And you can detect transiting planets. So this is a sensitivity map for Roman, I think a 30-day run at 16th magnitude, where you can actually start to detect small planets, the sub-Neptune sized planets, which are much more common than hot Jupiters. Hot Jupiters have been shown using HSD to be really rare in globulus, but I think this could be a very exciting way to sort of push exoplanet science into old Milky Way populations for the first time systematically. Okay, with that, I will leave with my summary, and I think I already talked a bit too long, so I'll just stop there and take questions. Thank you.
All right, thank you very much, Dan. That was an incredible whirlwind tour.
That was the point, so
yeah.
I'm glad you interpreted it that way.
So we have time for a couple of questions. So on Zoom, just raise your hand and I'll call on you. And in the room, please use your seat mic.
Great talk. So for the TESS stars, the 160,000 stars, you already got mass for them, or like what is the state of that, and like ages? Or...
Yeah, no, good question. So the only thing we've measured for these stars is the one single parameter, the nu max parameter. So the center of this broad envelope of the oscillations. So the only thing that gives you is the surface gravity with a bit of a temperature dependence. So basically we've measured surface gravities for all of these, and then we took Gaia derived radii for all of them to back out the mass. So we have mass measurements. We have not gone the step of converting these mass measurements to ages, and one of the reasons for that is that I don't think we have spectroscopic abundances for the whole sample. So that's one of the things that we'll have to consider going forward. And I think some of the efforts will be for spectroscopic follow-up will be using the target list that we've published.
So how many stars actually have spectroscopy?
Yeah, good question. I should probably know this, but I don't. We did look, actually, one plot that I did not show, and I don't even have in my backup, is that we did cross-match with Apogee, and we did do the alpha over iron plot in mass spins, where you nicely see that, you know, for lower masses, you get the high alpha population, and then it moves down to the low alpha population. I want to say that it's maybe a quarter or something like that, some tens of thousands of them. But one of the main goals of putting this paper out relatively quickly was to inform the spectroscopic follow-up, so we can get spectra for all of them and actually do the next step of getting ages. Yeah, great question.
Any other questions in the room or on Zoom? Sam?
So kind of related to that point, are there any stars where we can actually measure astroseismic ages with TESS, so where we can actually measure the small separation? And do you think that number will get larger with longer baselines in the future?
Yeah, it definitely will. So the small separation that I mentioned at the beginning, that doesn't really work for red giants. It mostly works for main sequence stars. And the reason for that is the core structure, as you go from hydrogen core burning to hydrogen shell burning. So I think for the main sequence stars, there haven't been as many results yet. And that's because doing the translation from seismic parameters to fundamental parameters like age is a bit harder, but also the yields are lower than they are for the red giants because there's a lot more detection bias. I think the 20-second cadence data will really make a lot of progress on this. So for the 20-second cadence data that I showed, we did actually do that. We measured the individual modes, including, actually for those two stars, we did measure the small separation. And that's how we got those 10% ages for these stars. It won't be as many. I mean, if you put me on the spot now, I would say it would probably be a few hundred, where we can get really good ages that are main sequence stars and subgiants. So it will be much smaller than the red giants. And that's for the exact same reason as it was for Kepler. For Kepler, we had 500 main sequence stars and subgiants and 20,000 red giants. So I expect it will be a similar, perhaps, sort of scaling for TESS in the end. Yeah.
So I have a question. So what do you learn from the large frequency spacing, and would there be any benefit to measuring that in TESS data?
For sure, yeah.
And what are the limitations that make it hard?
Yeah, so if you measure the large separation and you believe the connection to the square root of the mean stellar density, and you have the new max parameter, you can calculate radii and masses. You can calculate a mass without relying on Gaia. It is actually an interesting question whether you still need that in the era of Gaia. Joel might have some opinions on this as well. Where you actually have to, yeah, it's a valid point. If you can measure new max and you believe your Gaia radii, which, you know, there's no reason why the radii shouldn't be accurate, and you believe your new max calculation, you can just get the mass out and get the age that way. I mean, this is for red giants. For main sequence stars, it's always better to measure frequency spacings and to get the density out that way. Actually, so one other argument why you want to measure the large separation is that it gives you the density directly. So if you're interested in exoplanets, that's super helpful if you want to get eccentricities of planets from transit light curves alone. So this is the work that Vincent Van Allen did for the Kepler sample. And I think we'll be able to do this at least for some fraction of stars also with TESS. There's been a bit of a dearth of astroseismic host star detections with TESS. You know, with Kepler, we've had a lot, but with TESS, not so many yet. This paper actually included, it's not shown here, but included Pi Men, which was the first transiting exoplanet TESS is detected. So I think, again, that this will be sort of, the situation will be better once we mine more 20-second cadence targets where the photometric precision will really help with backing that up. But that's another reason why you can directly measure the density, and that goes into the modeling of the light curve.
Awesome. We have time for one more quick question in the room or on Zoom. I see Adrian online.
This is barely a question, but first of all, great talk. I really, really enjoyed it. Thank you. But going back, you showed a figure of the sky with Kepler and K2 and TESS planets.
Yeah.
Very near the end. And my eye catches overdensities near the LMC. And I'm wondering what's up with that.
Yeah. I
Or
think
are you
that's
sitting on a huge number of exoplanet discoveries in the LMC that you're just not telling anyone?
I don't. To be honest, I don't actually know where I took that from. It might be a simulated population and not a real one. I'm not entirely sure. I think it's related to the continuous. I think it's related to the continuous viewing zones of TESS. So the LMC. So the one thing I know is that the LMC is in the continuous viewing zone, which is the one area in the ecliptic hemisphere when TESS is staring at that it stares in continuously, so there's no gaps, and probably that's where the TESS yield is planet is higher, just because you get longer time series and you back out longer period planets, and probably also some smaller planets. So, but yeah, good observation.
All right, I think we should probably leave it at that. So let's thank the speaker again. And then